In this video, I want to discuss what images are and the task of image classification. Because as you know, convolutional neural networks actually operate on images. So you give it some kind of image, you give a convolutional network a kind of image, and it'll produce something like a class label. It may produce, something like a bounding box around some object. So not only will it say that, oh, this is a picture of a dog, it'll tell you where the dog is in the image. You can produce all sorts of things with convolutional neural networks, but the key thing about them is that they operate on images and that they treat images as actual images and not what we did with artificial neural networks where you just kind of stretch it out into a vector. But we'll get to that when we discuss convolutional networks. But before we talk about those, we obviously have to discuss what images are and how they're represented in a computer and how we can perform different operations with images. And so first let's discuss what are actually images. So you've seen them all the time on your computer, on your phone, but how are they actually represented in a computer's memory or on a hard disk, for example? And so we're not going to get into like how they're stored on disk or in RAM or something. Anyway, we're just going to talk about them at kind of a high level. So you can kind of think of an image as being a grid of different pixels, and you can represent that usually with a matrix or with something we call a tensor. I'm going to show you pictorially kind of the difference between the two. So they're all different kinds of images, and we're gonna mostly been dealing with these types, and so I'll just discuss some of these real quick. So for example, the data that we discussed with the MNIST data is actually called binary image. So those are like 28 by 28 pixels, and each one of those is either on or off. So either the value is going to be 0 for off and 1 for on. Now, kind of one step above that is grayscale images, and they actually take on 256 possible values from 0 to 255, where 255 is white and 0 is black. And I should mention that these are integer values. There's no fractional, you can't have a pixel value in a grayscale image of like 8.75 or something. In general, you'll notice that these pixel values are generally going to be integers, although in some cases it's actually nice to convert them to floating point values, because later when we discuss how we perform different operations, especially convolution, and how we apply those, you can generally scale. We generally scale the 0 to 255 range inclusive to a 0 to 1 range, and that's with floating point numbers, but we'll get to that a bit later. So both of these cases, binary and grayscale images, it's kind of clear how we can arrange them in a matrix fashion. So like 20 by 28, for example, each value in the 20 by 20 is going to be 0 or 1, and same for grayscale, but it'll be from 0 to 255 inclusive. But how do you deal with color images? You see them all the time. I'm sure you've heard of RGB. It's a really popular one. But there are also other different kinds of color called color spaces or color models. They're different kinds. But so how do you represent that? Because that's like saying each pixel has its R, G, and B value. So it's kind of like, well, each pixel is in the matrix is actually a vector, and this is actually exactly kind of what a tensor is. So let me use a picture to show you. So on the far right there is I have like a representation of a grayscale image, and this is just an m by n matrix, and where we only have one value. That's what that last dimension is. So the first two dimensions, the m by n represents the spatial dimension of the image, and then the 1 here represents that I just have one value here. Now compare that with my RGB image. I still have the same two dimensions, the m by n, and then I have by 3, and this is what's called a 3 tensor, because I have three different dimensions. And so it's kind of like if I took one matrix and I stacked it on top of another matrix, and I stacked another matrix on top of it. Now I no longer have like a flat matrix. I have a volume, a 3D space. And so in order to index this, I need three numbers. I need the first two numbers tell me where spatially in the image I'm looking at, and then the last one tells me what color channel I'm looking at. So these are so uh, what's actually going on here is I store all my red values in one, I store my green values in another channel, my blue values in another channel, and then this how they're actually shown to you. The colors are like kind of blended together, and so like when you see a color that isn't pure red, pure green, or pure blue, it's actually a combination of that light coming to your eye. But anyway, that's what's called a 3 tensor. So anyway, that's a little bit about images, but let's get into a little bit about image classification. So the point of image classification, kind of the whole purpose of it, is given an image, I want to know what the image is of. If I give an image of a dog, I want to know that this is an image of a dog. And there's lots of challenges with this. So one thing is like, so I just listed a couple of them here. One is there's variations in scale that can happen with an image, whether you see a bus that's far away in the distance or a bus that's really close by. They're both still categorized as like buses or cars, but just because they're far away, we don't want to classify them as different things. Another thing is the positional there's positional variance in this, and meaning like where is the car in the image? We don't really care where it is in the image. We want to know that there is a car. And then there's this problem of occlusion, where if I cover up half of the car, I still want to know that this is a car. So kind of the old way of one intuitive way of thinking about this to build something called a k-nearest neighbor classifier. So this is actually really intuitive. You just store all of the training examples that you're given, and when you're given a new example, you have some distance metric that you compute, and you take that image and you compare it to all of your training examples in the past, and you use some distance metrics. Like for example, you might use the quadratic cost or something, where you look at each pixel corresponding pixel value and you compute that quadratic cost and you sum them all up over the entire over all of the pixels in the image, and that gets you a single number that represents how close one image is to another. And then when you do that for all your training examples, you can say, let me select the k, or like suppose k equals 3. So let me select the top 3 closest images to this new image, and whatever the majority voting class is of those 3 images, that will be the class of my new test example. So if I take an image of something and I run it through my KNN classifier, and the top 3 images happen to be one of the top 3 images is a cat, one of the other top 3 images is a dog, and the last top 3 image is a dog. Well, the majority vote here is dog, so this new test image must be a dog. So this is kind of like the intuitive way of maybe doing this, but it turns out that this is not really used at all, because one reason is you have a very long testing time to do this. In other words, there's no real training that's going on. You're just taking the new testing image, and you have to compare it against all of your training examples. So if you have a training set of like 60,000 images, for each new image and each new test image, you're comparing it against 60,000 images. So that's not really efficient at all. In practice, we want these deep learning, these neural networks, to have very quick test time. So the training time can be long, that's fine, but the testing time and evaluation has to be really quick. And another kind of point here is that occlusion changes or illumination changes can really confuse the nearest neighbor classifier depending on what kind of distance metric that you're using. So if they have that quadratic cost, and if you just take the if you take the image of a dog in low light and the image of a dog like outside, it might think that these two things are very different for the quadratic cost, the quadratic error function. So again, like there's lots of challenges with using just a KNN, so that's probably not the best approach to take. And so what a better approach would be is to, instead of storing the entire image, why don't I look for certain features that are representative of a particular class of images? So if I was looking for dogs, maybe I would look for like a specific kind of ears, or I'd look for like paws, and I'd look for a tail, and I'd look for like a nose, and these are the things that I would kind of look for if I were trying to classify a dog. Now, one important property we want these features to have is they should have the property of translational invariant, or they should be shift invariant. Means that no matter where in the image these features are present, we still want to count these as being features. So that means, like if I had a picture of a dog that's slightly left of the center of the image and one that's slightly right of the image, the center of the image, those would still be classified as the same thing. And most importantly, these features should actually be learned from the data. We shouldn't have to hard code these features. I shouldn't have to look at through all the different classes and say, oh well, let me come up with some hard code some features for a dog and hard code some features for a frog or a cat or So I shouldn't have to hard code these features. They should be learned from our data during our training process. So how we actually do this is, so let's suppose, just for now, that I have some features that I want to test manually. And so right now, let's just consider how we actually look for these features. So suppose that I have some feature here, and we call this thing on the bottom left here, we call this a filter or a kernel. Those words are interchangeable. It's basically something that detects a particular feature. So in this case, you can have one that detects different kinds. So in this case, this will detect lines or edges. And so this might be an example of something that after I train my network, I get back something like this, saying that, well, images that go to this class tend to have this kind of feature. And so we'll be discussing, actually, I'm going to stop right here, and then in the next video, we'll be discussing an operation called convolution. And that's how we can actually see whether or not a feature is present in an image. And so we'll be discussing convolution in the next video.